days, you more or less, I'll say more, have an idea of how they work, right? So far, you've seen it. You know what's inside. So I'm not gonna waste your time a lot there, but just know that those electromechanical relays usually come with either a name or some sort of information that you can actually go and look for the variations that you might have. And so you energize, de-energize. You've been doing that already. And the contacts, how they work, normally closed, normally open, all that good stuff, you've done it. So we're going to rather quick. Um, there is usually a difference here um, between a motor contactor and a control relay. So usually labels like that are going to be on the schematic. M for motor, CR for control relays, which is the one you've been using. All right, there's the relays again. And you guys did some of this already, which is, how do you how do you use the contacts so that you can indicate whether the system is on or off. There's a little demo on that. And you've done not the programming aspect, but the hardware aspect of it. And so that's the next part. And then I think I briefly mentioned about contactors. This is the heavy power loads, things that are used for moving large loads. I'm going to give you a brief demo. At some point today, I got my station kind of working back, and I have one of these large power loads, heavy duty contactors. Remember that I told you that once upon a time when I was learning about PLCs, I connected a load and I burned the PLC. And you don't want to do that because PLCs are, again, control devices. They are good to control small loads that at the same time move big loads. So never ever you want to connect a motor. Well, you can connect a DC motor like what the ones we've using, right? But not a large, AC induction motor directly to the PLC contacts because it'll be a little bit too much. So here it is, the contactor. Essentially what the PLC does is just like being energizing that coil on that electromechanical relay, the PLC signal will energize the coil terminals, which at the same time make this giant contactor actuate. So you control the coil on that large contactor that controls the load, right? And so that's how we actually take advantage of the automation part of controls. All right, motor starters. It's another kind of a method that you actually have. So in this case, we have a contactor. It's actually a Allen Bradley brand. And we have an overload relay, which serves as a safety device on the motors. So that if there's an overload, like you say, you have a 5 HP motor, and eventually the load exceeds that amount, this overload relay is going to sense that load. It's going to open up the circuit and hopefully protect everything. Here is a three-phase magnetic motor starter. See how that's wired? So on the upper part, the blue color is the control portion, which is also called the low current control circuit. On the lower hand, you have the high current power circuit. And observe here that we have three phases, L1, L2, L3, which go to the three-phase motor. But what is really making this happen is your low level voltage control, right? Until you energize the coil of that electromagnetic contactor, nothing is going to happen. So again, the PLC is not controlling the load; it will be controlling, your electromagnetic contactor. So here is a program, and what's involved in a ladder logic program. You're going to have start, stop, the motor auxiliary contact, and then the overload part, right? Which you want that overload to open up the ladder program if anything happens, right? If any high load beyond the load of the motor is sensed, then you want that to be open. So That's that. Again, same idea here. This is just a simulation of the process. Okay. Manually operated switches, there's a lot of those. We talk about them a little bit early on. Normally open is usually for start, normally closed is usually for emergency. And then you have some NEMA type, which are of the type make break, right? So you have to press to activate them. You press to open, you press to close. And so those are some of the types that you can have. You also can have a selector switch that will be used for multiple positions. An example of that is when you want to put your system in auto mode, you want to put the system in off mode, and then in manual mode or hand mode, as is said. So multi-selector switch. You also have deep switches, which are used when you have, various kinds of loads or inputs that you want to put into the system, right? They're called deep or dual inline package. We actually use them a lot in electronic circuit, especially digital or microprocessors. If you want a specific binary count to go in, you just select the switches, like in this case, right? 1 is selected, 2, 4, 8, 16, and 32 is selected. So that means that 65 is the decimal count on that, right? Binary wise. All right, mechanically operated switches. Again, there's a lot of electromechanical switches, including limit switches, and run switches is another word that is used. Hi, Constantine, how you doing?
Good, how are you?
Welcome. I miss you. And so these are different kinds of limit switches. And again, the concept of normally closed, normally open, it's on all electromechanical control blades, right? Just be mindful that a normally open contact means that it needs to be energized to be closed. A normally closed contact means that when energized, it opens, right? So that's a concept we've been talking about. Temperature switches, those are switches that will activate or actuate based on sensing temperature, and they will open or close depending upon what their normal default status is, but they will actuate with temperature, right? And the thermostat is always an example that is brought up for that. You also have pressure switches of different kinds, and they actually can control air or liquids, and they can also be either normally closed or normally open. Compressors, chambers, boilers, and things like that use this type of switches, pressure switches. You also have level switches that you can use to sense liquid levels. And again, the idea of, normally open, normally closed is going to be there. All right. You also have sensors, which, generally speaking, we're still talking about discrete components, right? And is everything that sends a signal to open or close a circuit, or a signal to say, yes, I'm turned on or I'm turned off, right? And so proximity switches can be categorized in a separate group. And the reason being, there's usually solid state electronics involved in those sensors. All right. Depending on what is being detected, you can have various kinds of sensors. One of them being an inductive sensor. That's proximity sensors that are used to detect both ferrous metals and non-ferrous metals, right? So that will be a inductive type. And there is a little bit of principle of electromagnetic field inside, which is at work. Okay, I want to move this a little bit out of your way. All right, so those are inductive sensors. We talked a little bit about this early on, how you connect the various switches based on how many wires you have. Like in this case, we have a 3-wire sensor, and that's how that's going to go. Usually you're going to have a little bit of a paper schematic data sheet for those switches, and you just connect them the way they come, or it's just various kinds of way to have those loads connected. You also have proximity sensors that will sense a range of distance. They usually are equipped with an LED status indicator to show you when the sensor is on or off, energized, de-energized. This idea of leakage current is something to keep an eye on, and there's usually a way to fix that, and that's what they call using a bleeder resistor, right? So that bleeder resistor takes care of that leakage current, and the leakage current could be a problem because it's almost like, you're trying to send, a liquid or a gas to another place, but at the same time you have a leak somewhere in the pipelines. You don't want that. So in the case of electrons and protons, we actually use a bleeder resistor for that. You also can have capacity proximity sensors, which they also operate on electrostatic field, and they can be actuated by both conductive and not conductive materials. So when you put the target near the sensor surface, it enters the fields and then changes the capacitance of the oscillator. You can sense metals, non-metals with that. They will sense metal objects as well as non-metal materials such as paper, glass, liquids, clothes, and so on and so forth. They're usually used in some form of a production line. Okay, magnetic reed switches is another popular type of switch. It's got two flat contact tabs that are sealed in a glass tube. And when there's a magnetic force that is generated parallel to the reed switch, the reeds will draw together to activate as a switch. So magnetism will close those ridges. And is usually caused because the object, it's metallic, right? There's actually a number of applications that you can have for that. You could have a moving part that is being sensed by the reed switch, or you could have a moving part that is moving the reed switch and activating the reed switch, opening and closing the reed switch. Magnetic reed float switch, that's another type that you can actually use for magnetic purposes. You can also have photovoltaic or photoconductives that are other types of switches. I mean, a popular type of this is the photocells in the streets, right? Our lights go off at the night in the daytime and on in the nighttime because of the photovoltaic sensor switches that you have on those street lights. This is another type photoelectric sensor. You're going to have a visible or invisible beam of light that will respond to a change, right? And you're going to have two pieces in it, transmitter and receiver. And it's also called optocoupler because you actually couple a couple of electrical signals. Scan techniques, methods to use by photoelectric sensors to detect an object, right? The car washing system is one that uses quite a bit this type of, through beam with scan techniques, right, for detection of the car when it's entering in. You also can have a retroreflective scan, again, housed in the same enclosure, right? Different kinds of switches, right? Fiber optics are other types that are actually used today for various applications. One of the main ones being, some sort of a communication, but fiber optics have changed the life. I mean, we got all kinds of automobile cabling system with fiber optics, the medical equipment with fiber optics. There's a lot of applications in that area. Barcode scanners are the eyes of data collection systems. So that's another method of, a PLC potentially scanning products or boxes using barcode scanners. You can also have ultrasonic sensors, right? They're used in robots in industrial processes to detect, different objects and things that are happening. They're usually analog, right? We talked about the analog measures, which is going to be a measure of voltage or current. In this case, 4 to 20 milliamps. And 4 means 0, and 20 milliamps, well, 4 means 5 inches of water there, and 20 is the maximum. So that's how that works. Strain gauges, I'm sure you probably have done some experimental work because you guys do a lot of material stressing and stuff like that, right? Mechanical engineering, and so you could use strain gauges to collect data from strength of materials and things like that. All right, thermocouples also are used as temperature sensors, right? And we know that basically you have a joint that you heat up, and you're gonna have a change of difference of potential as that is heated up. All right, resistive temperature detector (RTDs) are other type. You're gonna have a resistance that's gonna change with temperature, whether that's positive coefficients or negative coefficients. So those other type. Flow meters or flow measurement devices, which are inside liquids or fluids, that are also part of this group. Tachometers, generators that you're gonna use to convert rotational speed into some form of analog signal that can be used to control an application, special analog application. I think we talked about this encoders a little bit, optical encoders, and how you can actually use them for purposes of taking some action, making some tasks. All right, these are some of the standard symbols for the various control devices: pilot lights, control relays, motor starters, motor overloads, alarms, heaters, solenoids, solenoid valve motors, and horns. And I think these are some of the most common ones used in industrial applications. You're going to have all sorts of actuators that will be used as an output. A solenoid is one type of actuator, actually a very popular kind of actuator. A solenoid is to either open or close the passage of something liquid, water, fluid, air, whatever. All right, so solenoid valves are very popular. Here's an example of a solenoid valve that controls a lot. When I first learned about PLCs, one of my instructors teaching me PLCs was a guy whose job was to oversee the operation of a production line of gas in Wisconsin. And so they had all sort of PLCs and solenoids all around the cities where they distributed the gas, right? And so, they could detour the passage of gas, close and open, from their office using the solenoid valves. Stepper motors, which are very popular in industrial controls, are actually also part of the outputs. All right, you can have a motor drive a stepper motor, whether individual stepper motors of a form of an automated system like a robot. All right, and how that works is you divide the revolutions into number of steps, and the motor will be set the voltage pulse for each step. And then you have the rotation, which is proportional to the number of pulses, and the speed of rotation, which is relative to the frequency of those pulses. So you have pulses, you have frequency, and then you can determine the steps of a stepper motor. You also have servo motors, which are relatives, but they do operate on a closed loop mode, while the stepper motors operate in an open loop mode. So in other words, the servo motors will have some form of feedback that will help that motor do its work. So servo motors. All right, so more on servo motors. There's all kinds of various applications. There's a controller, there's a servo amplifier, there's a servo motor, there's the load, and there's the feedback. The device that sends feedback information back to the servo amplifier or the controller. All right. All right, we're moving real quick. This is something you already are familiar with. Part of what you've been doing is the control part of this. We haven't done the power part, but you've been doing, and you have now an idea of the memory or seal-in circuits. Work with those, right? You all have an idea about that. Here's an example of a simulated seal-in application for a conveyor system. Okay. All right, motor seal-in circuit implement using the Allen Bradley Pico controller. That's a very tiny controller you can put in your hand, right? And usually you even program that thing on that little screen. So that's a Pico Allen Bradley. All right, we didn't get to do this part, which is actually the last part of the handout that I gave you. I don't know if we're going to do it or not, but here's a schematic diagram for that, and that's an interlocking circuit. When you have a machine or system that you want to rotate in two directions, you don't want nothing to happen while the machine is running in one direction, right? It'll be awful that you go in overdrive and eventually put reverse, right? You know what's going to happen. So the same idea here. Um, it's a interlocking circuit, a safe circuit. All right, here's how the interlocking circuit will be implemented using ladder. Observe here that as the first run is running, somehow the second run should not be able to run, right? Because of this auxiliary contact. And likewise on this one, right? This one will not run if this one's running. So that's an interlocking system. Here's a little program on how we do that. With the RS Logic simulator. All right, so you can have this idea of interlocking, whether physical or software based. So in this case, the circuit prevents solenoid A and solenoid B from being energized at the same time, right? We just want one of them to be energized, not both. Here's the simulation for it. You can only have one at the same time. That might be the same situation when you have a machine that rotates in two directions. All right, lashing relays. Lashing is momentarily energizing and holding the relay in the latch position. And then you have the unlatched coil, which momentarily energizes to disengage the mechanical latch and return to the relay of the unlatched position. So we also have software-based lashing instruction, which is the OTL with the L and OTU with the U. So you can latch on and unlatch an instruction which at the same time will execute an output. Here's an example of a hardware and program latching circuit. All right, so when input 1 is on, the circuit latches. And if you can see here, the advantage of this type of instruction is that it doesn't require any auxiliary contact, right? Because the latch itself does the work. And then when you turn it off, you unlatch it. They both have the same address because they're referring to the same output. So that's the latching instruction. And the unlatching. All right. We saw this example early on of a process used to control the level of water in a storage tank. I don't think it was as elaborated as this one, but here again we have at least 7 inputs, actually 4 inputs, on, off. Okay, and then the manual and auto. And then you have the low sensor switch, high sensor switch, and then you have the indicating lamps. Okay, and here is the program for that. We have manual, auto, manual, auto, manual, auto, repeated. I think some of you asked about, repeated commands. Here's an example how you could use repeated commands for the same purpose. So that's the program. There's the I/O connections. You're gonna wire your sensors or inputs to the input module, and then of course you're gonna wire your outputs to the output module based on your ladder program. This is a pretty nice simulation of a water level control system. Okay, and this is the main part. So we're gonna stop here, we're gonna do it. So here's the sequence control process. That's a bottle filling applications. The task here is to fill the bottle and press on a cap. And so you have to have an order. Combination controls require that certain operations be performed without regard of the other. All right, here the tasks are: one, place the label on the bottle; two, place label 2 on the bottle. In this case, the order doesn't really matter, right? You can do label 1 or label 2, whatever the case might be. You also might have automatic controls where you want to maintain a set point, right? And if there's any deviation from that set point, you're going to have an error that will compare against the set point, and you're going to have a correction factor. Here is the sequential process control, right? You're going to start button. You're going to start that. The table motor is going to get started. The package is going to get moved to the position of the limit, and automatic is going to stop. So that's a sequence. And this is how it will be implemented, right? Start PV1, then the relay is energized. It's going to move, and when it reaches the end, it's going to stop. So that's a sequential process. There's a simulation for it. And here again, the IOs are simulated by this switches, switch inputs. All right, the search instruction referring from the most likely to be false to the least likely to be false. We talked about the sequence of operation. A jogging circuit is a very popular type of circuit which allows you to reposition the machine to a certain spot you want. And so notice that they just added a momentary button here that will allow you to energize the circuit and jog it. Okay, so here again is the jogging circuit. Kind of a special application to when you want to be able to have control over the machine. Sometimes running the machine and stopping will not stop it where you want it versus jogging the machine. That's a good application. All right. Here is an operation, a drilling process that requires the drill press to turn on only if there is a part present and the operator has one hand on each of the start switches. That's a semi-automatic operation. So 3 conditions have to be met, right? The part has to be present. Both hands of the operator have to be on for the presser to drill the hole. So that's the input, that's the output, and that's the actual ladder logic program. Okay. Here's an overhead garage door that is operated automatically to preset open and close position. Here's the motorized overhead garage door ladder logic program. A nice simulation. Okay. Continuous building operation. So you're going to have boxes moving on the conveyor, and they need to be automatically positioned and filled. And so there's various things that are going on here, right? The indicator lamps, the motor moving the conveyor, the solenoid on the hopper, and then the sensors and switches. So that will be the ladder logic equivalent. We got our inputs, we got our outputs, and we got the ladder logic equivalent.